Hi, how are you? Dr. Shiva here. I hope that all of you are doing good and all of you are in good health. Today we're going to continue the last topic, and this is the last week as well for me to teach the vector calculus, and this is the last topic whereby we're going to concentrate on the Stokes theorem, and many of you did ask many questions, and I hope that I will address all these problems in my tutorial lessons. Okay, I will address all the your questions. Okay, I will address your questions in my tutorial lessons. Therefore, today I will concentrate in the Stokes theorem, and since Stokes theorem is one of the can be considered one of the integrated theorem whereby we integrate the curl and the surface integral together, and we're going to analyze the problem of what we call surface integral. Okay, in a way that we're going to analyze the vector field and the work performed on the any surfaces. Okay, let me continue with the for the Stokes theorem. Okay, Stokes theorem, it's required lot of concentration. Okay, concentration. Therefore, every okay, hold on. Okay, Stokes theorem. Okay, Stokes theorem. Let me before I explained the application and the what you call the overall aspect of the Stokes theorem, let me introduce to you the definition. Okay, the definition of Stokes theorems. Then slowly I'll try to compare, and we're going to analyze in depth the idea, then the theorem in detail. Okay, let me introduce first the theorem. Okay, if F is a vector field, okay, the existing is a vector field existing over open surface and open okay surface. It's a kind of called open surface. We're going to use this term open surface. I will use this word open surface. It's very important. And around it's a boundary closed curve C. Then okay, this is the formula. Okay, we're going to see this formula, which is FDR equals to a surface curled F dot ds, big S, and or we can write this as a curled. Okay, we're going to use a curl and the small s. Okay, we have done. Okay, this is the definition. Okay, again, if F is a vector field existing over an open surface S and around its boundary closed curve C, then we can define, okay, you can see the path integral. Okay, you can see this is a closed loop. Path integral is equals to curl F ds. Okay, this is the definition. Okay, now what am I going to do? I'm going to explain this systematically, and as you all know, we already learned before. Let me explain part by part, then I'll go into detail. Okay, and we have learned this Stokes theorem actually is another advanced stage of what we call the green theorem. Okay, I'm going to let me explain first. Okay, we know this is the work, right? The work on the path. Okay, path integral. Okay, path integral. Path means here C, right? The curve. Any curve, then this is must be a closed loop. Okay, this must be a closed loop. Okay, now we have learned something about the Green theorem, right? Okay, Green here, the Green theorem. Okay, the Green theorem in 2D, we call it maybe as a sun. Okay, the Stokes theorem. The Stokes theorem. Okay, the Stokes theorem basically. Theorem is for to explain the 3D, and maybe I may call it that as a father. Okay, it's not we are trying to create here the relationship, but there is a very close relationship between this Green theorem and Stokes theorem, whereby the Green theorem will explain not only the second D, it enable us to use the Stokes definition for the second D, 2D environment, and Stokes theorem is a one stage advance, and which it will able to support the 3D environment. Okay, now you won't understand what I mean by 2D and 3D. Let me go through with you step by step the idea of this Stokes theorem. And first of all, the very important message that I wanted to emphasize here. Okay, I wanted to emphasize here. Okay, there is a two message that I wanted to really you need to have a complete clarity, on this, whereby you should be able to explain the open surface, and one more word is a closed curve C. Okay, we have learned this in a Green theorem. Okay, closed curve C. Okay, the boundary with the closed curve C. But open surface S. Okay, open surface S is something new to you. But closed curve C is understood, right? Okay, normally the closed curve means is we know anything that can move and in the closed loop. Okay, in the closed loop, it's not an open loop. Okay, now let me go one by one. Okay, let me go one by one. Okay, first of all, we learned something called del F, or we call it that as a curl F. Okay, what the curl F will do? It will able to explain the rotational field, the state of rotational field. Okay, but if we say the curl of F is a 0, then immediately we know it's a irrotational. Okay, the field is irrotational, and I just add some more messages called conservative as well, or another state that we can immediately, if we can say this is a irrotational, it will be a conservative, and it's once we say it's a conservative, it's automatically we call that as a path independence. Many of you did ask me what is potential. Okay, independence. Okay, independence. Okay, independence. Okay, now the first thing is irrotational. What is the difference between irrotational and rotational? Okay, irrotational means the vector field is something in a rotational form. Okay, you should be able to see something like this. Okay, the vector field, it's a kind of slightly rotational. You can see here. Okay, this is the vector field it's a kind of rotating, kind of in the rotational state. This is rotational. It's not irrotational. The irrotational means, okay, the vector field. Okay, the vector field will look straight. Okay, no rotation. Okay, the vector field is conservative. This is what we call it as a conservative or irrotational. Okay, this is a irrotational. The vector field is a irrotational. Okay, with this understanding, earlier we did study something about two things. Okay, what are they? Maybe I can be able to write here. I hope that it's quite clear to you. Okay, for any closed loop, earlier we learned for the Green theorem, for any closed loop, okay, closed loop, that means it's a closed curve. Okay, curve C, line integral. For the line integral, closed loop line integral, okay, two conditions we did apply. One, okay, is a closed loop. Okay, the second is a conservative. Okay, we did learn something called the path integration. Can you guess what is the path integration solution of this? Okay, can you guess or not? Okay, if it is a closed loop and conservative, what is the solution of this? It's a 0. Okay, it's a 0. Why is 0? Because once it's a irrotational or conservative or path independence, immediately we will call this as the work. Okay, over here the work, if you calculate the work for this, is a 0. Okay, this is what we learned. Okay, now if in one more case also, if it is a conservative, okay, if it is a conservative, then we learn something, one more important message. There should exist a potential function. Okay, there should exist a potential function where f, okay, the gauge must be equal to f. This is what we learned. For which case, again if we know for the any closed loop line integral, okay, if it is a closed loop and it's a conservative or closed loop, if it is a closed loop, of course it's a 0. If it is a conservative, I forgot to say it's a conservative, there should exist a potential function for any conservative function, for conservative f, okay, where f equals to, for any conservative f, whereby f here, and we will say f here is a potential function. Okay, potential function. Okay, I already told you, if it is a conservative, it's automatically, you see I'm moving back to the path integral again, but if it is a conservative, it's automatically, it's understood, it's a path independent. Path independent means we no need to worry. For example, if there is a to the B, if it is a, okay, something moving from A to B, for the case, okay, FDR, okay, it's not a circle, not a closed loop. This is not a closed loop. We can say F, okay, B, this is B, okay, this is B minus FA. You should get the results for the path independent. If you don't get it, okay, let's say A, this is B. If something moving like, oh, okay, it's a path independent. We don't care whether Okay, you are moving by bicycle or you are moving by these things. If it is a W1, if W2, this is what we call W1, W2 must be the work that has been done here. Okay, in these both cases will be same. Okay, will be same. Therefore, this is what we learned so far. Okay, and now I'm going too far away from what I supposed to teach you. Okay, now this is for the revision. Consider this is a kind of revision that suppose you need to able to get the able to solve once you see these things. If it is a path independent case, if the question is if it is not conservative, if it is not conservative, that's where you will see but closed loop for this is 2D problems. For 2D problems we use I use a common layman message lah. Okay, use Green theorem. Simple. Make it as simple as possible. If it is not conservative but it is closed loop for 2D problems, we use Green theorem, right? This is almost all of you will agree with me. Yes, we did learn. I don't know, I call it this as a method 8 or what, but as long as you know it's a Green theorem, we use this technique, right? Now I'm going to introduce how do we combine the logics of this, and we're going to bring it that for this is a 2D case, right? Okay, now let me put it to you this in detail. If it is a F, if it is a closed, remember it's not conservative but it's a closed loop. Can I write this? Yes, you can write. You are allowed to write. This is a closed loop. If it is a closed loop, FDR, and if it is a del Q or del X, del P or del Y, if it is for the area, okay, area, or sometime we will write this as a opposite. We just bring it out via negative, and del P, del Y, del Q, del X or dA, both are can I say both are same? There is a slight difference only. Flow in, flow out. That's the difference. I don't want to go so much detail in the physics of this. Okay? But later in mathematics, you can identify yourself how to interpret this logics. I'll teach you that. Okay? Once you get negative, you need to change your direction. That's it. Okay? What I mean by that, for example, your solution is negative. For example, okay, let's say this is the circle, this is the circle. Imagine, let's say the polygon works like this. Okay, it's a closed loop. Let's say imagine this 1 2 3. Okay, A to B, C, let's say. If it is a okay, if you get the solution, okay, if the solution is positive, okay, this direction is correct. Okay, this direction is correct. But okay, the direction is correct. Okay, I'll just say correct. Direction is correct. Okay, but if the solution, okay, is negative, then you need to change the direction. We need to change the direction, okay, of the loop. For example, if this is the case, right? Okay, we need to change the direction. That is the message. Okay, therefore the difference is, as you know, it's a flow in, flow out, but it's a direction. Okay, it's basically we are talking about the direction. Okay, once you get the negative, it doesn't mean you are wrong. Okay, but you must understand that you must change your direction. That's it. Okay, you know the work basically will be defined, and somebody asked me also, how can suddenly you get this negative f dr? What is this? We never learned this before. Okay, some student did ask this question. They say, oh sir, this is negative. How can suddenly negative coming in for the column charge calculation and etc.? The message is simple. The message is one, the negative basically is a explanation of the decrement or the change of direction. That's it. Okay, you must understand this process. Don't get panic. Don't say this is not a definition. Okay, but you must understand this is a changes of the direction. Okay, works always is a positive, of course. Okay, but when we say negative, it means we are in the different direction. We are using a different direction. For example, if the force and times with this is actually positive, sometimes it's a negative, means we are using the opposite side of the direction of f. Okay, this is the understanding that we have for the work. Okay, now based on that, okay, let me explain further. And from here, this conclusion for the Green theorem, we understood one important message here that we agreed, everyone, which is we say del q with the del x not equals to del p and del y. We call it this as a non-exact. Okay, it's a non-exact. Okay, non-exact. This is the message that I wanted to emphasize here. Okay, we are still explaining the non-exact process here. Okay, if it is a not conservative, non-exact means is not a conservative. It's not a path independent. Therefore, but one more condition it's fulfilled is a closed loop. It's a closed loop, but it's not conservative. You must see this two words. Okay, it's not conservative, but it's a closed loop. If it is a closed loop, then we will say this is a non-exact. Okay, non-exact. Therefore, we will use Green theorem to solve the problem, right? Okay, can you understand this process? Okay, similarly, we use the same thing for the advanced stage, whereby we use, okay, for the 3D, okay, we can use both. Okay, here you can see we will use curl. Okay, curl for the 3D environment. Okay, and explaining the same thing, the same curl, which is basically is a loop, closed loop. Yes, we can use a closed loop. And very important, you must remember, is defining here dr, and we are still referring to the work. Okay, but the work is for the 3D environment. Okay, therefore you must remember, if f is a 2D environment, you directly can use FDR, Green theorem. Remember, this is a very important message I am trying to deliver to you. I know you won't understand now, okay, but later I'm going to use these logics very much. Okay, try to understand this. If the case is when you notice, how do I know? You may ask me this simple question, sir, I didn't get it you exactly. What you mean by 3D, 2D? I don't understand, because you see, how do we differentiate whether it's a 2D problem or 3D problem? In what way we can differentiate that? Okay, very simple, the F. Look at the F. I didn't I didn't put it here. What is F, right? If let F equals to, here Pi Qj, okay, plus PQR, RK. Okay, when it become a 2D, if there is no for the F, there is no RK. It's a 2D. This is referring to the 2D. Okay? Okay, without K. If you just happen to see P and Q in the F, you need to use Green theorem. Okay, simple, huh? You got it, huh? Another one, for the 3D, if F involves Pi, Q, J, RK, then you need to use 3D. Okay? To calculate the same work. Okay. Now, then I hope that you can understand this for the moment. Okay, I'll show you the example. I will show you the example step by step. Okay. So far, can you get it? Okay. Now, I hope that you can follow me. Can you? Okay. Now, this is a little bit extensive topic. Unlike divergent. Okay. This is a little bit very extensive topic. Okay. Let me start with the simple example. Okay, simple example. Example 1. Okay, can you see that? Oh, sorry, huh? Okay, if it is in the first example that we're going to see one simple analogy here. Yes. Okay, XY, the ghost. Okay, we're going to see one simple analogy in this particular case, 0, 0, 4. Okay. Okay, let me put it to you first. 2D, and are we going for the 3D first? Let me introduce to you 2D. Come on. Sorry. Okay. This is not okay. Come on. Okay. Now, can you? Okay, the camera is, come on, focus. Okay, okay, focusing is becoming some problem here. Okay, suddenly focus becomes something issue here. Okay. Okay, in this particular case, okay, now, let me put it to you, one simple question. A surface consists of 5 sections formed by the planes. Okay, formed by the planes. Okay, x equals to 3, 0, 3, maybe a 0. Yes, 0 equals to 3, and y equals to 0, y equals to 2, z equals to 0 and 4. Okay, now only just now I did stress to you the word called open surface. Okay, now unlike in divergent theorem, okay, remember I'm going to compare now. Unlike the divergent theorem, all the surfaces of that polygon will be closed, but in the Stokes theorem we will assume one of the surface of that polygon is open. Virtually, I may say, is a virtual open. That's a very important word that I would like to stress here. It's a kind of virtual open, we call it. I don't want to say that it's a kind of virtual open. What I mean by virtual open, that's an important question that you will ask. Virtual means something, okay. There will be a 5 segment. One segment is what do you call we tied, okay, we tie with the any solenoid, for example, any solenoid, or maybe you didn't get it. Okay, maybe wait, I will explain to you in this question. Okay, let's say we sketch this first. Okay, I will explain here. Better I will explain by example, then it's easier. And the gauss is actually f equals to x minus y, right? X2 yj. Okay, enough. Maybe I start with the 2d, huh? 2d. Okay, this is a 2d. Can you see f is a 2d? Okay, immediately. But can you see the problem that we're going to solve here is a 3d? Can you see that this is a surface consists of 5 segments formed? Can you see this? Okay, let me put it to you. This is a 3D problem, and z and y, and this is a x. Okay, how to sketch that? Okay, the sketching of this. Okay, kind of we need to. Okay. Okay, now let me call it this as a, and this one is the coordinate for the x is here 0 0. Okay, what about the coordinate over here is b. Okay, coordinate you can identify by yourself, and the c a b c is 0 2 0. Okay. What one more? Maybe I here define here D. Okay, D is clear, and it is ED, E, F, G, H, where the H is 0 0 4. Okay. Can you see there are 5 surfaces? Okay, now I stress this part. They say the surface consists of 5 segments, okay, formed, but in this particular case the question is not complete yet. I need to say one segment is open. Okay, I open, make it this open. I don't have any red pen here with me at this moment. Okay, can I use something, red pen or something like that? No. Okay, imagine this surface here over inside here. Okay, let I may say A, B, C, D is open. Just now I mentioned as what? Open surface. Okay, open surface. And you must remember, if it is an open surface, it also must come together with one more information. Open surface as and around. This is very important. Its boundary. This is what I call it virtual, closed curve C. This is what I want you all to understand. Okay, can you see this word? Okay, again, let A, B, C, D is open surface S and around. Okay, around its boundary closed curve C. Okay, this is what I wanted to emphasize to you very closely. I want you to monitor this process. Okay, whereby you see there is something called C1, C2, C3, C4 curve. There are curve moving around one surface. This is what we call as a open surface. Why I call it is a virtual. Okay, why I call it? Okay, that means, remember, unlike for the divergent theorem, in the Stokes theorem, you will have indefinitely. Okay, you must remember. Okay, if this kind of scenario, if you face this kind of scenario, is automatically understood. You must use what you call Stokes theorem but not divergent. Many students confused with the idea when they start looking at any volume of polygon, okay, polygon with a volume or 3D, immediately they started thinking about what you call divergent theorem, Gauss divergent theorem. But you must remember, if A, B, C, D, they will provide to you. Don't ask me again this question, but I just stress to you, in any circumstances, they will give you one open surface S and around its boundary closed curve C, like this. You should see. Maybe it can be like A, B, F, E, can be. But in this case, it's given. You will be given, not you cannot by yourself assume. You cannot by yourself assume. What I mean by that, okay, they place the solenoid here, okay, in a polygon. Okay, they place a solenoid here. For example, I'm giving you an idea. Okay, therefore, virtually this part, this section, okay, called A, B, C, D, we will say virtually, I call it virtual. Okay, it can be open. Okay, no problem. It's absolutely open, but the idea is a open surface. We call it as a open surface S. Because why is open surface S? Because its boundary is close with the curve C. Okay, the curve C. That means it's encircled with the, or encircled or tied, or maybe it's surrounded with the what we call as a kind of solenoid. Okay, it could be solenoid or anything. Okay, as long as the charges moving around. Okay, the charges or anything, the electrics. Okay, moving around. In this case scenario, we call it that as an open surface. Do you get me or not? Okay, I already spent more time to explain this, Okay, this is what we call as an open surface and around its boundary closed curve C. Okay, because I know this is very important, but at the moment you may find it, oh, why am I, putting this much of effort to explain this again and again. Okay, but it's very important. Okay, with this, we will consider this sect as an open surface. Open surface, okay, open surface, it exists. Okay, you can see it's open surface exists. Okay, you can imagine this is a solenoid moving around. Imagine it's a kind of you can imagine there might be some solenoid or any charges moving around. Okay, any charge. Okay, it may carry anything, electricity or whatever, but the best explanation is solenoid lah. Okay, it can be a solenoid or moving along, okay, along this line, moving along this line. Okay, you can imagine anything that moving around in these circles. Okay, okay, now you imagine there is an open surface. I call it as a virtual. Okay, with this, okay, now the solution for this, okay, you must take note on that. In a simple, we will write this as a, okay, it's a closed loop. How do I know it's a closed loop here? Why is closed loop? You see, can you see this? It's a closed loop. Okay, the open surface, which is with a closed loop, okay, closed curve. This is, imagine, it's a closed curve loop, maybe. That's much more better explanation. Open surface, closed curve loop. Okay, okay. Now, if this is the case, okay, this is can I use a green theorem? Yeah, but see, we need to use Stokes theorem. Okay, Stokes theorem. Okay, what it mean by this? Okay, in this case, we need to use this. I forgot to create the 5 standard segment. There are, maybe let me create the segment first. Okay, in this particular case, okay, let me write this because space is important. Okay, now I will write this. First C1, you need to take a C1 for the FDR. Okay, or C2 or C3 at, okay, path integral for C1, C2, C3, C4 is equivalent to, okay, surface. How many surface are we having here? 5 only. Okay, we integrate with the S2, okay, S3. Can you see that? Oh, am I not clear? Wow, the space also is not enough. Okay, 4 plus S5. Okay, can you see this? S5 altogether. Okay, C1, you need to equate this to the surface. It means, okay, remember which one is segment 1 and this one, without the segment except the segment of the open surface. Maybe you may ask, what is S1, S2, S3, S3 for a while, huh? Okay, this one, okay, this part, since it's a closed loop, you can see this is a closed, right? We can use, if it is a 2D, if it, since it's a closed, right? Okay, if it is 2D, if it means it's here F. If F is 2D, okay,